This class covers Chapter 5, Mechanical Properties of Engineering Materials. There are two general categories of materials properties. Mechanical properties are covered in Chapter 5, and physical properties are covered in Chapter 6. We'll talk about physical properties in the next class. The difference between these two general categories of properties is mechanical loading. Mechanical properties describe how a material reacts to an applied force. Physical properties include everything else. So, if you stretch or squeeze a material either once or multiple times, either gradually or rapidly, the material changes shape and maybe even breaks. We can measure how much it stretches or compresses. We can measure how much force is applied, the energy to break it, or the number of cycles it takes to break it. The everything else category, the physical properties, includes a lot of neat stuff. It includes properties used by the medical products industry, like the shape memory effect. A phase transformation in certain types of metals can cause the component to change shape in a predictable manner when the temperature changes. Physical properties include properties that we use in thin films, like coatings on windows that transmit light but reduce heat loss. This is a big deal in the window glass industry because of environmental regulations in Europe and North America. Today, we're talking about mechanical properties. The most common mechanical property that we measure is hardness. We typically push a hard indenter into a sample and then measure one of two things: how deep it goes or how wide the resulting indentation is. Stanley P. Rockwell worked at a ball bearing manufacturer, and he needed a good way to measure the hardness of bearing races. The indentations with a Brinell test were too big, so he developed a brand new testing machine. The picture here shows a typical Rockwell tester from the 1920s. In the hardness testing lab, we use a Rockwell tester to push a 1/16 inch diameter tungsten carbide ball into the sample, applying two loads, called the major load and the minor load. The minor load sets the ball down hard on the sample, and the major load presses it in. The machine determines the difference between these two depths and converts it to hardness. Rockwell tests use a variety of indenters, hardened balls from 1/16 to 1/2 inch diameter, or diamond cones for harder materials. Loads range from 60 to 150 kilograms. These tests are called regular Rockwell hardness tests. Sheet metal can be tested on a Rockwell tester, using much lighter loads of 15, 30, or 45 kilograms. These are called superficial Rockwell hardness tests. Rubber is tested in a similar way with a durometer gauge. These gauges will fit in your hand and have a spring-loaded indenter. The deeper the indenter goes into the rubber, the softer the material. In the hardness lab, we also use a Brinell tester to measure the hardness of metals. We push a 10 millimeter diameter tungsten carbide ball into the specimen and measure the diameter of the crater. The wider the crater, the softer the material. Brinell hardness testing doesn't work for sheet metal because it's too thin. Knoop and Vickers tests use diamond indenters and produce a square or diamond-shaped indentation. You measure the distance across the indentation. For example, the micrograph at the right shows a cross-section of a low-carbon 1020 steel that has been case-hardened. The surface has a hardness of about 61 Rockwell C, while the interior has a hardness of about 26 Rockwell C. The surface is at the top. You can see that the Knoop indentations are wider toward the bottom of the picture, where the material is softer. Look how small these indentations are. 200 microns is 0.2 of a millimeter, or 0.08 of an inch. The indentations are less than 130 microns wide, 0.005 of an inch, and they're spaced about 75 microns apart. That's 0.003 of an inch. You can't do that with Rockwell or Brinell hardness tests. So if you want to measure the change in hardness in a coating or through the thickness of a piece of sheet metal, this is the way to go. The actual numbers in hardness tests have a physical meaning. These equations are in the textbook. Brinell hardness is a function of the applied load, F, the diameter of the ball indenter, capital D, and the diameter of the indentation, lowercase d. Vickers hardness is a function of the load and the average of the two distances across the square-shaped indentation. Knoop microhardness is a function of the load and the longer dimension of the diamond-shaped indentation. Rockwell hardness is a function of the change in depth as the hardness test is run. First, you apply a minor load. In the case of Rockwell B and C, the minor load is 10 kilograms. In theory, the indenter goes into the metal a little way. Second, you apply a major load from 60 to 150 kilograms depending on the test. This pushes the indenter much further into the metal. Third, you release the major load and maintain the minor load. The metal relaxes, recovering its elastic deformation, but the permanent plastic deformation remains. The change in height between the two applications of the minor load in millimeters is used to calculate the Rockwell hardness. There are similar equations for the other Rockwell scales. There are portable hardness indenters that measure how high a steel ball bounces off the test material. These hardness testers are not as accurate, but because they're portable, some consultants like to use them. What you really have to watch out for is results converted to a standard scale. Hardness tests should always state whether they're actual readings or converted readings. In 1812, the German geologist Friedrich Mohs invented one of the first hardness scales. The way this works is you scratch the sample with a variety of different materials, ranging from talc to diamond. The hardness of the material is determined by what will scratch it. The scale is not linear, but for geology that's okay. We don't use the Mohs scale for traditional engineering materials, but it is used for some ceramics and some ingredients of ceramic composite materials, like the grit used in grinding wheels and sandpaper. One of the reasons we check hardness of a metal part is so we can compare it with specifications to see if it's what we paid for. So if you check hardness on a Brinell tester, but the specification is in Rockwell B, then you've got a problem. Fortunately, all the major hardness testing companies publish posters with conversion tables. The problem with these conversions is they are materials specific. The conversion between one scale and another depends on the material being tested. So the conversion for brass will be different from the conversion for aluminum, which is different from nickel, different from steel, and so on. The American Society for Testing and Materials, ASTM, publishes many conversion tables for different metals. Modern microhardness testers have built-in conversion software, but they're usually set up only for steels because that's what most people use them for. But if you are measuring the hardness of a different material, you've got to be careful about accepting the conversion that the software spits out. We have other methods of measuring hardness of non-metallic materials. Rubber hardness is measured with a durometer, similar idea to Rockwell. You measure how deep the penetrator goes into the test specimen. Wood hardness is measured on the Janka scale. A 0.444 inch diameter steel ball is pressed into the wood to 1/2 its diameter. The force required is the Janka hardness. The strange thing about the Janka hardness test is that the force has different units in different countries. Pounds in the United States, newtons in Australia, kilogram force in Sweden. The values shown in the table are the side hardness, where the ball is pressed into the side grain, not the end grain. Janka hardness is used mostly for flooring as a measure of scuff and gouge resistance. The two mechanical properties we use most in strength of materials, ET200, are strength and stiffness, which is also called Young's modulus. Here is Young's original definition of modulus from 1807. The modulus of the elasticity of any substance is a column of the same substance capable of producing a pressure on its base, which is to the weight causing a certain degree of compression as the length of the substance is to the diminution of its length. Do you understand that? It's pretty confusing. Engineers in 1807 didn't understand it either. The response from the British Admiralty was, "Though science is much respected by their lordships, and your paper is much esteemed, it is too learned. In short, it is not understood." It took 50 years before engineers accepted this idea, because Young defined modulus before stress and strain were invented. Today, we define it as the slope of the stress-strain curve, stress divided by strain. And you can see from the graph that steel is stiffer than aluminum. It has a bigger Young's modulus. Let's take a look at a tensile stress-strain curve. When you stretch a steel sample, the stress and strain are proportional to each other, up to some limit, the proportional limit. We don't usually use this property, but it's a very real point on the graph. If you stretch it a little bit more, you'll reach the yield strength of the material. If you were to relax the sample, it would return to its original shape, like a spring, with no permanent deformation. We call this elastic behavior. If you stretch it beyond this point, the metal will permanently deform. We call this plastic deformation. For many metals, the yield strength can be found by drawing a construction line offset at 0.2% strain off the straight line portion of the stress-strain curve. Once we go beyond the yield point, the metal permanently deforms. This is what we do when we bend or stretch metal in a manufacturing process. It's usually undesirable in a finished product like the hood of a car, except that in an accident we do want the hood to buckle and absorb some of the energy of the crash, so the energy isn't absorbed by the people in the car. The tensile strength, also called the ultimate tensile strength of the metal, is the maximum stress on the curve. If you keep stretching the metal beyond this point, its cross-sectional area decreases significantly, and that's what we call necking. On this curve, we're defining stress as the load divided by the initial cross-sectional area. So as the area decreases, the stress will also decrease until the part breaks. We're usually not too interested in where the breaking point lies because we never really want to see this point during service. Once you're past the ultimate tensile strength, you're in big trouble no matter where the final fracture occurs. When a ductile metal is pulled on a tensile test, microscopic voids form inside the test specimen. Because there's less metal in contact, the specimen starts to neck and more microscopic voids form. They join up to form a crack running horizontally through the test specimen. When there's not enough material left to support the load, the specimen shears off at a 45-degree angle, resulting in the so-called cup and cone fracture shape. During a tensile test, one portion of the tensile bar will neck down and the diameter is reduced. You can see this in the sample in the photograph, that the cross-sectional area is smaller where the final fracture occurred. The sheet metal forming industry and the wire drawing industry want to know how much the area can be reduced before the part breaks. We can calculate the reduction in area by taking the difference in the areas. A sub F is the final cross-sectional area, A sub O is the initial cross-sectional area. Some metals, like low-carbon steel, have two yield points. We call them the upper yield point and the lower yield point. So why does this happen? Think back to the second lecture where we said that deformation is about dislocation movement. Also, we said carbon atoms fit in between the iron atoms in steel. When dislocations start to move, carbon atoms interfere with this movement, driving the yield point up a little. Once the dislocations get moving faster, we get a lower yield point. The main reason we're looking at this phenomenon is someday you may see a stress-strain curve looking like this. It doesn't mean there's an equipment failure. It's a real phenomenon. Tensile tests cost money for sample prep and for testing. Sometimes we take a shortcut by measuring hardness and estimating the strength. The textbook has a couple of formulas for estimating ultimate tensile strength of steels from Brinell hardness. There are other formulas available for other hardness scales and materials. What you have to remember is the accuracy of these formulas. They'll often get you in the ballpark, but the numbers can be within plus or minus 20%. So take the estimate with a grain of salt. It's only an estimate. Let's think about what happens when we push an indenter into a piece of metal. The indenter's ability to deform and penetrate the metal depends on a number of factors. Number one, friction between the indenter and the sample. A low friction material like leaded steel or leaded brass behaves differently than a higher friction steel. Number two, the difference between tensile and yield strength values is where all the deformation occurs. So if there's a large difference between those numbers, you can have more deformation. Number three, Young's modulus and yield strength determine how much springback occurs. When you release the load, the metal partly returns to its original shape. So the crater isn't the same size and shape as you release the load. Cast irons are much weaker in tension than in compression, so the relationship doesn't work so well for cast irons. If you want to correlate cast iron hardness with some kind of a ultimate property, it would be ultimate compressive strength, not ultimate tensile strength. In the lab, we're going to do torsion testing of solid round samples, but you can get more accurate results with a hollow specimen like this one. The section in the center is the part that actually twists, so we call it the test zone. It has length L, average radius R, and wall thickness lowercase t. Capital T is the applied torque. This is not a cheap test specimen because it requires a lot of machining. Here's the math behind a hollow torsion specimen. The shear stress in the test zone, Greek letter tau, is force over area, which is the same as torque divided by area times the lever arm. And the lever arm is the radius in this case. The cross-sectional area of a thin-walled tube is the circumference of the tube times its thickness. When we multiply everything together, shear stress is torque divided by 2 pi radius squared thickness. The shear strain in the test zone, Greek letter gamma, is radius times the angle of twist divided by the length of the test zone. And the shear modulus is shear stress divided by shear strain, in the same way that Young's modulus is tensile stress divided by tensile strain. So let's work out an example. Capital T torque is 400 foot-pounds, radius 0.6 inches, thickness is 50 thousandths of an inch, the sample twists 0.42 degrees, and the test length is 1.5 inches. So using the factor label method of unit conversion, we always start with the algebraic expression, then plug in the numbers in units, and then tack on the unit conversions at the end. For shear stress, the unit conversion is feet to inches. For shear strain, the conversion is degrees to radians. So we have a shear stress of 42,000 psi, a shear strain of 0.0029, and when you divide the two, you end up with a shear modulus of 14.5 million psi, which is stiffer than steel, but not as stiff as chromium. The next mechanical property we'll talk about is fatigue, because we're almost at the end of the lecture. Fatigue is different from the other mechanical properties because it takes place over a long period of time. If a part is loaded below the yield strength multiple times, tiny cracks can form in the material. Microscopic scratches in a material's surface or microscopic inclusions or defects inside the material can concentrate the stress locally to the point where it exceeds the tensile strength of the material at the crack tip, and the crack will grow. So a crack forms, and the tip of the crack acts as the stress concentrator, and if we don't do anything to stop it, the crack will keep growing until there's not enough material left to support the load. Fatigue is important in applications where the load changes many times. Rotating machinery, such as axle shafts, gear teeth, and bearings, are susceptible to fatigue. Bicycle spokes are susceptible to fatigue. Bolts and rivets under cycling loads are susceptible, as are pressure vessels under cyclic loads. In fatigue testing, you apply a load, you release the load. You apply it, you release it, and keep on going until the part breaks. There's a diagram in the book of the earliest fatigue testing machines for rotating axle shaft materials, and we still run rotating bending fatigue tests that same way. So you record the number of cycles to failure, and then you try again with a different load, and if you collect enough data, you can generate what's called an SN curve, where S is stress and N is the number of cycles plotted on a log scale. The cartoons here show two different behaviors. On the left, the longer you run the test, the lower the stress level is needed for failure. This is typical of aluminum alloys. If you run an aluminum part in fatigue for long enough, eventually it will fail. On the right, the curve flattens out. If you keep the stress levels below the fatigue limit, the part will never fail in fatigue. This is typical of steels. You can design steel parts to never fail in fatigue. What the cartoons don't show is the scatter in the data. The longer you run the test, the more scatter you get. Scatter is often more than one order of magnitude, so no other mechanical test has this much scatter. We expect tensile test results to be within, say, plus or minus 5 to 10%. Hardness tests typically within 1 or 2 Rockwell points. When I worked in the lab in the light axle division at Dana Corporation, design engineers would wander in from time to time asking us to explain why the scatter in their fatigue data ranged by a factor of 5 from lowest to highest. And we would tell them that they were darned lucky. A factor of 10 is the best you can usually hope for. The reason the engineers' data didn't have more scatter is they didn't run enough samples. If you apply a load below the yield strength of a material but above half of its absolute melting point, then the specimen can plastically deform over time, and we call this creep. So what's the absolute melting point? It's the melting point using an absolute temperature scale like kelvins or degrees Rankine. The largest example of creep on the planet are glaciers. The melting point is 0 Celsius, 32 Fahrenheit, but on an absolute scale, 273 kelvins. Half of the absolute melting point is 136 kelvins. Glaciers are substantially above that temperature. The load is caused by the weight of the ice upstream, or up mountain. Glaciers flow around bends and curves, over rocks and through valleys without breaking up into tiny pieces. They move as solid blocks of ice that deform as they move down a mountainside. In this cartoon of strain versus time, a tensile specimen is pulled on a tensile tester under a very low load below the yield strength of the material. The specimen is surrounded by a small laboratory furnace to keep it hot, and the amount of strain is recorded versus time. Eventually, the specimen will break. Now, this rule of thumb of half the melting point is not a firm rule. Lead will creep at room temperature, which is below half its absolute melting point. Nickel superalloys are designed to creep at 70% of their melting point or higher. This is a big issue for jet engine builders. The last property we'll discuss is impact. We'll be doing impact tests later in the semester. The idea of an impact test is to measure the energy it takes to break a sample. Test equipment hasn't changed much in 100 years or more. We use a pendulum and swing it at the sample. The potential energy of the hammer is its mass times gravity times the height. The energy absorbed during fracture can be measured by the final height that the pendulum achieves. There's a lengthy explanation in the chapter, along with a history of impact testing. I will talk about it in class later in the semester, just before we run the impact lab. So, to summarize, these are the main points touched on in class number 3. Mechanical properties measure the response to an applied mechanical load, while physical properties include everything else. There are a number of hardness test methods for different materials. Young's modulus is a measure of the stiffness of a material. Stiffer materials don't deflect as much under an applied load. Steel is stiffer than aluminum, so a steel diving board won't deflect as much under a swimmer's weight as an aluminum diving board having the same dimensions. You can pull on a solid material with a certain load, then release it, and if the stress was below the yield strength, the material will return to its original shape. If you pull it past the yield strength, then you'll permanently deform the part. Cyclic loading below the yield strength can cause fatigue cracks to grow until the part finally breaks. High temperature loading below the yield strength can cause the part to gradually plastically deform over time. And impact testing is done at high speed, and we'll focus on this property later in the course.